I'm really excited to be at Data Council and talk to all of you about our architectural journey at Hex. And hopefully there's some stuff that's interesting here to a bunch of you. Why don't we dive right in? Thanks for the introduction, Carlos. I have really been privileged to learn from a lot of very intelligent people in my career journey at the places that Carlos mentioned. What drew me to Hex in particular is I really love the intersection of interesting product problems and interesting technical problems where you only get to the right solution if you consider both sides strongly. And Hex has that quality in spades. I was really drawn to the vision of what Barry, Caitlin, and Glenn were building there, and that's why I'm here. And I haven't painted my hair pink yet, but I'm hoping to get there soon, one thing at a time. So how many people have used Hex? That's awesome. That's awesome. I'm going to spend a little bit of time just showing you what Hex is. Here is a sample Hex project. It's Data Council, not Dumpling Council. One thing about Hex is we spend 50% of our time thinking about or eating or analyzing data related to dumplings. Very important. So this is a view of what a Hex project looks like. Inspired by notebooks and literate programming, you can do SQL queries like this, and then you can connect the result of that SQL query to a Python cell, and you can directly call pandas code on that data frame and then get that result. Then you can do another SQL follow-up, and you can basically chain cells together to do whatever analysis you want. And then you can add a chart at the end of it. And then ultimately you can find pieces of this and publish them. These projects form directed acyclic graphs that connect all the pieces together: SQL code, visualization, other no code, Python, etc. So that is just a taste of the product. Let me put it back in presentation mode. Our vision is that it's a platform that anyone can use to ask and answer questions for data. You can explore data, you can analyze it, you can collaborate with other people, you can collaboratively edit it, you can publish, and it's all the same platform. And the important inspiration from literate programming, which is Donald Knuth's term, is it follows human thought, and it must be inherently flexible in how you put things together. So when we say multimodal, what do we mean? In Hex, everything is a cell. I showed you a couple of the cells just now, and here's a snapshot of another graph of cells. And those cells allow you to cross language modality, Python cells or SQL cells. We have our support as well. Interfaces like tables, charts, pivots. There are inputs. Also, there was a question about federation. So federation in Hex is possible. You can connect to different warehouses. You can connect to CSV files, other files, all in the same project. So this is all built on this concept of everything being a cell, and every cell takes inputs and produces outputs. So a project is basically a DAG or directed acyclic graph of cells. So the product problem, the architectural problem here is how do we let you run DAGs of cells? I want to talk a little bit about the power of multimodality, just in another example. So a little bit of a video here to show you how analysis chains. So starting from a SQL result, you could do a no-code filter cell, which might be the easiest way for you to filter for California. You can do a SQL query on top of that. Then you may want to chart that result. And you can actually filter your chart down to the time range you're interested in, and then use the chart to output data that goes into a pivot table. It's not typical for you to consider a chart as a thing that outputs data, but it's doing munging of data just like many other things are. And so that is the flexibility of a multimodal analysis, where you can just think through and add step by step what you need. We're also thinking a lot about natural language and interacting with these cells in different parts of the product. So we have an Ask Magic feature that we've been developing where you can ask a natural language question and it will give you back a new cell type we've built this year, or actually last year, called Explore. And the Explore cell gives you the ability to slice and dice data in many ways, but it's also a cell that you can put in a notebook. It's also a cell you can publish and share in a data app to a stakeholder. So this flexibility is power. And I think Knuth here says it best. The language that you express your ideas in has a strong influence on the thought process. So we believe a multimodal foundation allows you to follow the approach you find most intuitive. And what's really interesting is that in a world with AI, agentic analysis, that's all coming up quite a bit these days. What's good for humans is also good for the robots. There are so many tools at your disposal in a multimodal framework that you can ask agents to try all of them and see which ones are best at giving you the answer you need. So all of this just redoubles the need for an architecture that can allow you to do this kind of mix and match assembly of different things, different modalities, different languages, all in one place. So that's the vision that we are chasing. So the compute architecture, this is the main focus of this talk. How do we do this? So remember, our goal again is execute any DAG of cells, however it is composed. Our CTO, Caitlin, gave a great talk in 2022 Data Council talking about reactivity, which is running the part of the graph that needs to be updated whenever you make any update. You don't always have to rerun the whole thing. So I won't talk about that today. What I will talk about is how to do things in parallel and how to manage state. This gets quite complicated when you are managing Python, SQL, tables, charts, all these different things at the same time. All right, so as I said, at Hex, we think a lot about dumplings, dim sum, things of that nature. So here's a very simple project that describes a very simple analysis on orders from a dim sum restaurant. So we have a SQL query to get the orders up top, and we have two branches of this graph. One where we're looking at the dumpling orders, and we want top dumplings per city. So we do those SQL queries, and then we have a chart for that. And then on the right side, we're looking at noodle orders specifically, and we're actually going to run a noodle sales forecast in Python on all the noodle orders, and then we're going to plot that noodle forecast. So this is a simple project. Hopefully that makes sense conceptually. I'm now going to walk you through how this executed in our original architecture. So let me explain what's on the screen here. The directed acyclic graph is on the upper left, so you can follow along with how the execution goes. Project state on the upper right. We are architected around the Jupyter kernel. How many of you have used Jupyter notebooks? Probably a good number of you. Yeah. And I'll show on the bottom left the queue of things being executed in the Jupyter kernel. So in our original architecture, the source of truth for everything is pandas data frames. Pandas data frames are going to be captured inside the Jupyter kernel. We do use DuckDB. DuckDB is great. We love the DuckDB team. You can use DuckDB directly on pandas, and that's how we would invoke it here. Every cell would generate Python source code. So that's what allows you to basically do a Jupyter execute request cell by cell. And because of how Jupyter works and because Python is not thread safe for objects, if you've heard of the global interpreter lock, pandas as a library is also not thread safe. We don't do anything in parallel in this architecture. It's all sequential. So let's walk through this. So the first SQL query was to get orders. So we will get an orders data frame, and it's in the kernel. And now SQL cells 2 and 3 on the DAG can be queued for execution. We can only do one at a time. So next we will do the dumplings query and get that result and put it in the kernel. Then we'll do the noodles query and put that in the kernel, and we're building the graph as we go. This is a breadth first traversal of the graph. Then we do the top dumplings query. Then we run the noodle forecast, and all these data frames are populating in the Jupyter kernel. And then finally, we have two charts that get outputted one by one. So hopefully straightforward. This is how the original architecture worked. Not parallel. We want this to be parallel. But I just told you a bunch of things about how Jupyter is limited in how parallel it can be. So what do we do about that? The rest of the talk is literally how to break out of this and do more. If anyone here knows mythology well and sees the words Jupyter and breakout and sees the bow and arrow, that should immediately indicate a particular name, which you'll see later in the talk. Small mythology quotes. Okay, we tried to do parallelism in Jupyter actually. So one thing you can do, it's not like Python doesn't do multi-threading. You can do multi-threading in Python. What we wanted to do was not block inside Jupyter while you're running an expensive data warehouse query. So we split the command to run that warehouse query into 3 pieces: a prepare, an async dispatch, and then a wait. And as long as you can send all of the async dispatches together, then those can all be running in parallel in the data warehouse without the Jupyter kernel being blocked. And that was the idea. So here's a sample project where you have a Python cell that just has to run. It's not connected to anything particular. And then you have 2 queries to the data warehouse. And I've split out this XYZ, prepare, async, and wait for these. And now we have our Jupyter kernel executing stuff over here. It depends how you order things, whether this works or not. If you order things in the following way, let's say that B Python cell is actually kind of expensive. If you get all your async executions queued up before that B cell runs, then both of your warehouse queries can run in parallel without getting stopped by anything, no problem. However, if you don't order it correctly, let's say you send the things for query A, but then you ran that Python cell B and B happens to be slow. Now you can't even enqueue the async query for query C, and now you haven't parallelized anything in the warehouse. You may not know how expensive this Python code is to run beforehand. So how do you know? This becomes something that you can't predict in how the project is going to run. So this is not a great approach that's going to handle everything well. So clearly, this suggests we should move more things out of Jupyter. What can we move out of Jupyter? All right, the first thing that we looked at was breaking data frames themselves out of Jupyter. We had a world where Jupyter kernel was our source of truth for all the data in the project. And we introduced a query caching service called TableStore, which was basically a blob storage that can also be represented on a file system. And now we have a way to store rectangles of data somewhere else, or results sets of any shape or form somewhere else. The Jupyter kernel can access this by mounting a file system and reading those files and then turning them into pandas if needed. But the problem that you have here now is you have state in 2 places. You have state in the Jupyter kernel and you have state now in this TableStore. And you have to keep them in sync all the time. That could be expensive and that could be annoying. So what do we do about that? Well, I've always found that the best engineers I've worked with in my career are inherently lazy people and they don't like repeating work. And I think the same thing actually applies here in that why do you need to eagerly sync everything between 2 places if you're not actually going to use it in both places? That's a relatively simple insight. Implementing it turns out to be challenging, so I won't be able to talk about all the details here, but I'll try to give you a taste. So the idea with this project, which we call lazy data frames, is that you only lazily sync what your Jupyter kernel needs. So here, for example, we had this query for all of our orders which hit the warehouse. The TableStore has the results of that query. The Jupyter kernel does not. It just has a reference that says it exists and it's in the TableStore. The second query was dumplings within the orders. Now that one is represented actually as a chained query. So it takes the orders reference and then it represents the query on top of it. It hasn't even been materialized. So it can be lazily evaluated when we need it, but it's just stored and left in this state. The noodles data frame is a data frame we needed to run Python on. So because of that, it needs to be in both places. So on demand, we had to materialize it and use it. So let's just walk through this in a little bit more detail so you can see it in action. Now, we haven't changed the fact that Jupyter is our source of truth on what's there. We haven't gotten rid of our single execution queue, but we are moving more state outside of the Jupyter kernel so we can gradually do more. So that first orders query, it again is going to run the query on the warehouse and then store a reference to it in the Jupyter kernel. Then we're going to run the dumplings query as basically represented as a CT and not execute it. Then same for the noodles query based on the orders. We're not going to execute that one either. Again, we haven't used the results of these yet. Just a small detail, in Hex you can see like previews of tables, so we will execute like a limit 20 or something like that to get a page, but we won't run the whole thing. Top dumplings of all the dumpling orders per city, same thing. This is also going to be represented as SET and not executed. Okay, so now something interesting happens. We have to run this Python noodle forecast, which needs the noodles data frame, and it produces a data frame. So now we need to materialize number 3. And we have number 3 in the kernel, and we have number three in the table store, as well as the outputs of that Python cell, the noodle forecast in both places. So we save it until that moment, and then and only then do we do it. And now finally, we need to run our visualizations on top of this. We need the top dumplings data frame now to be materialized because we need to show all of the top dumplings per city. So now that gets materialized. And then the noodle forecast is already available, so we can plot the noodle forecast. So that is how that works. By the way, I don't know how easy it is to interrupt me for questions, but if anyone has any confusion on this, please let me know. I'm happy to address it as we go. Okay. All right, so we got some things out of Jupyter, but we did not get to parallel execution yet. Checking how I'm doing on time. Okay, great. We did not get to parallel execution yet. So SQL can be executed in warehouses and DuckDB and any database in parallel very easily all the time. We've been doing it for decades. So why can't we do the same thing? This whole time we have been limited by running everything through the Jupyter kernel, which is the decision that came out of being inspired by notebooks. But as we're evolving the architecture, there's no need to be constrained by that. So we introduced a new component that we call Minerva, and that's the answer to my mythology riddle from before. So technically, Minerva is the daughter of Jupiter and was born out of Jupiter's head because Jupiter ate Minerva's mother, because mythology is weird sometimes. I also think we missed an opportunity to call it Minerva with a Y instead of with an I. We can still make that decision, I think, just to properly mirror Jupiter. Anyway, the Minerva executor is the thing that we can now use to basically run SQL. That's what it's for. So back to our project and back to the execution pathway here. So a couple of new components are going to come into the picture. We have the Minerva executor now, which has its own execution queue separate from Jupyter completely. And we also have state lookup outside of Jupyter, outside of the table store, kind of global to the whole project. One of the problems we had before is we had to keep checking in Jupyter for what's going on. What data do we have? What are the data frames? What's available? Where is it? So now all of that state we're taking out. And now we are not limited by the single-threaded nature of the Jupyter kernel anymore. Walking through this execution now, so our orders query to get all the orders, it now runs in Minerva and not in Jupyter. It doesn't need to touch Jupyter at all, in fact. We store the reference to it in state lookup, not in the Jupyter kernel. So, and then we also write down the result of that query in the table store. So now we have successfully removed the SQL query from Jupyter without losing the Jupyter kernel. And you'll see how it comes into play later because we need it to execute Python and other kinds of things that Minerva can't do on its own. Okay, so next we have two SQL cells that are descendants of this first SQL cell, getting the dumplings and getting the noodles. And now both of these can actually run in parallel in the Minerva executor. So you can see they're both on top of the executor there. And that brings in these two references for these two. I have not written down the whole CTE piece here just because there wasn't enough room on the slide. But these references have references to the queries. So when you need to materialize them, you can. Now, downstream of that, there's another SQL cell for top dumplings on the left, SQL 4, and then that noodle forecast on the right, Python 5. They're enqueued separately, and they can also run in parallel. So Jupyter can't run multiple Python things in parallel, but Jupyter and Minerva can run at the same time if they don't have a cross dependency. So that's what we do. So now a lot of things have happened, and I should speak to this a little bit more carefully. So the delta is as follows. So let's first talk about the execution of that Python cell. So it's taking this ref3 noodles, forcing it to be materialized, and then generating the noodle forecast. So what happens here is I've prepended a few things in front of 3 noodles to say what places you can find the data. 3 noodles you see is now in the Jupyter kernel and in the table store because we needed it in Python and we want its SQL copy to also be up to date. So it's being actively synced. And so JK for Jupyter kernel, TS for table store. The state lookup now tells you you find this data in both places if you need it. And similar for the noodle forecast, which was the output of that Python cell. The SQL cell number 4, which was just running on the dumplings and getting the top dumplings, that can stay a reference because we haven't used that in Python or Viz or anything. It can stay unmaterialized. All right. At this point, both Viz cells are reachable as next steps in the computation, and Minerva can run them both. In as much as a visualization can be represented in SQL, Minerva can handle it. Any cell that can be represented as SQL can be handled by the Minerva executor in this architecture. So there's a whole separate line of what things can be SQLized. As I was thinking about Lloyd's talk, I was realizing Malloy can be SQLized. So this architecture would also be able to handle that pretty easily. So the next step would be to run both of the visualization cells. And now we need to materialize the top dumplings data frame, and it's now in the table store. And so now we've executed the whole project, but this one actually ran in both tracks in parallel the whole time because we introduced Minerva and we introduced state outside. So that was the goal of adding these pieces to the architecture. Okay, very quickly, want to just show in an actual project what this means. So here's a benchmark project that we have been working on. It's about 70 cells. It's got, I don't know, 30, 40 charts and value displays in the app itself. And then this just gives you a sense of what the DAG looks like. And I'll show you what it actually looks like. It's basically a project to look at view data for the Hex product. It's a slice. This is not real data actually, but get a sense of computing all this stuff. And then we have a tab for January, we have a tab for February, we have a tab for March. We can slice this by customer and so on and so forth. So one of the big things that we're trying to do is move this more and more and more towards ultimately BI performance. So this is one important step that we've taken with the Minerva project, and we have a couple more things we're doing later this year that will get us closer and closer to very interactive performance. But that's what the app looks like. And now going back here, this is a side-by-side of running the project with Minerva enabled on the left and with Minerva not enabled on the right, which is our old architecture. So we're getting about a 2x speed up, introducing all of these parallelization and lazy evaluation constructs, which is something that I'm very happy about. Obviously, there's more to do, and there's more we can get out of this architecture, but we didn't lose the multimodality aspect of Hex. We didn't lose Python. We didn't lose all the no-code cells. We kept all of that. And our goal is to get us to the final point without losing all of those elements, because those are the things that make our product unique and flexible and powerful for more users. Okay, so here's a summary then. We started with something single-threaded where Jupyter was the source of truth that would eagerly materialize all data, whether it was needed or not. And we moved to something that was parallelizable, multimodal in how it was storing data, and did things lazily, so it could save computation and effort. Now, there's a lot of hard things in here I did not talk about, like interrupting and re-executing things, rate limits, fan out, security isolation, all the hex cells, DSL for cells. There's a lot more into this, but tried to do justice to the main points today. I just want to give a thank you to the great folks at Hex who helped us make this happen. And also the founders of Hex. I'm very privileged to work at this company. Carlos and Data Council for being great hosts, and all of you for being a wonderful audience. And I'm happy to answer any questions.